surface C, but it has also thickness epsilon in this direction, epsilon, 2 epsilon thickness. And in this tubular domain, you know from mathematical physics that heat conduction on such tubular domain is described by the Laplace equation. By Laplace equation. How? You take the energy functional, which gives you the energy of this heat conduction, energy functional, and the function which gives minimum to this energy functional is always the distribution of the temperature on the surface. And this minimum is found this way. You take the, well, here is described how the minimum is found. You find very easily that this minimum, the function which gives minimum to this function, is exactly solution of the Laplace equation. This is what happens in the tubular domain. Now, the last trend in mathematical physics is how to describe now what happens when you have thin surface. So thin surface you consider as some tubular domain is minus epsilon epsilon when epsilon is small. And consider the equations which you have here in the tubular domain, they are known, and then put epsilon to 0, send epsilon to 0. What happens then? Then you have not normal convergence there. You cannot consider it, the convergence in the normal terms because so the measure of your tubular domain becomes 0 from the point of view of the whole surface, whole space. Your surface has measure 0, so you cannot consider usual limit, but you consider so-called gamma limit. Gamma limit, you have functions, sequence of functions. You consider the limit, how to say, the lower limit of the functions, and this, if they converge, if they exist lower limit, which gives minimum to certain integral functional. So this convergence and is called gamma convergence. And we write, and we proved that if you send epsilon to 0 and consider this equation in the tubular domain and send epsilon to 0, you will get the solutions of this equation converge in sense of gamma convergence, converge to the solution of Laplace-Beltrami equation. So that means that at the end you get the heat conduction on the surface is described by the Laplace-Beltrami equation. If so, now makes sense to investigate such boundary value problem. So you have Laplace-Beltrami equation, which is the limit, gamma limit of our heat conduction equation in tubular domain. So now we can investigate this equation with Dirichlet, Neyman, and boundary, and Dirichlet, Neyman, and mixed boundary conditions. Here are conditions. So this L2 space, you know, the square integrable functions on the surface. This is W1, the Sobolev space when not only function belong to is square integrable, but all their partial derivatives. So it's Sobolev space. Function itself and all partial derivatives belong to L2. Then you have W1 space, and then the traces of such functions are in W half. I don't want to explain what those spaces are, but they are described very well. It's Sobolev-Slobodetsky spaces, so-called. On the boundary, you have on the boundary the Sobolev-Slobodetsky space. This is very rigorous formulation, but classical weak setting of the problem. Classical weak setting. And this is the conditions for the mixed problem. You will have such setting of our problem. We can also consider non-classical setting when not F belongs not to LP, L2, but certain Sobolev space, Sobolev-Slobodetsky spaces, and it's more general setting of the problem with Sobolev-Slobodetsky, and Bessel potential spaces can be involved also, and this is more hard to investigate. I will tell you why. So okay, first problem which we encounter here is the existence of such traces. The function belongs to this space, especially in the previous setting. When you have here, function phi belongs to this, and you take then trace on the boundary. Trace on the boundary of the normal derivative, it does not exist. But this problem is solved because our functions are solutions to the Laplace-Beltrami equation. We use the usual technique, the green formulae, and prove that these traces exist. So the setting is correct. First of all, first conclusion. Setting is correct, and after this we can formulate this theorem that these solutions to our problems exist and is unique for the Dirichlet problem and for the mixed problem. For Neumann problem, you need one additional condition on the function that the solution will exist. And this additional condition is written here, that the average of the function on the surface should be 0. If this is fulfilled, then you have the unique solution again. And how is this proved? For p is equal to, the proof is easy. P is equal to, we just apply in a proper way Lax-Milgram lemma. Lax-Milgram, famous Lax-Milgram lemma. And it works here, and the proof is only half page. That the solutions exist and are unique, and everything is done with the help of Lax-Milgram. But for the case of P between 1 and infinity and the general S and this non-classical setting, you have bigger problems, and then you need fundamental solution to construct the fundamental solution, to construct the layer potentials, representations, and they use this theory of pseudo-differential equations. It's much, much more complicated. But it is also done, but here it should be very, very careful. First of all, the first problem which you encounter here in this setting is that differential operators on the Rn, they are invertible always. If they are not 0, they have inverse. So that means the existence of fundamental solution. All differential equations on the surface, on the Euclidean space, they have fundamental solutions. This is Malgoraj-Ehrenpreis theorem, so-called Malgoraj. They always have fundamental solution, but on the surface, they have not. On the surface, differential equations have not fundamental solutions. They are not invertible. Why? Because fundamental differential equations on the surface, they have kernel. Any equation which you consider on the surface PD, u is equal 0, has solution u is equal constant. All constant functions are annihilated,